Find a differential operator that annihilates f of x equals 6x e to the power negative 4x plus 5 times e to the power x sine of 2x. So the annihilators that we want to use are the annihilator for x to the power k e to the power rx. The annihilator for that is d minus r to the power k plus 1. And then the other annihilator that we want to use is when you have e to the power alpha x sine of beta x. The annihilator for that is d minus alpha squared plus beta squared. So we need to figure out what r, k, alpha, and beta are in these cases. So for our first example, or first part of our function, we have the x e to the power negative 4x. So if we compare that with xk e to the power rx, we see the annihilator that we have to use for that is r equals negative 4, right? And k equals 1. So the annihilator for that first part is d minus 4 to the power k plus 1 is 2. And then for the second part, the annihilator we need for e to the power x sine of 2x, we see that alpha equals 1. That's the 1 in front of the x here. And we see that beta equals 2. So the annihilator there is d minus 1 squared and then plus 2 squared. Now, we have annihilator for this and we have an annihilator for this. Now, when we apply these linear differential operators in, we basically look at the composition of those two, we can just multiply them. So you apply this first on the entire function here that annihilates this part, but it doesn't really do anything to that, doesn't bring that closer to 0. But then you already have a 0, and then you apply this, and that will make the second part go to 0. So the annihilator is just the product of those two differential operators. So that's d plus 4 squared, and then multiply that by d minus 1 squared plus 4. So we will now examine how annihilators can be used to find particular solutions. So we're going to consider the nth order differential equation with constant coefficients, a sub n times the nth derivative of y plus a sub n minus 1 times the n minus first derivative of y plus dot 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 plus a naught times y equals f, where we can summarize the left part of the differential equation there by a linear operator, and that linear operator, that x on y, is given by a sub n times dn squared plus a sub n minus 1 d to the power n minus 1 plus dot 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 plus a naught. Now, if we use that notation, we can then rewrite this non-homogeneous differential equation as L of y of x equals f of x. Now, suppose that A is an annihilator of f of x, that is, A of f of x equals 0. We can then apply A to both sides of the differential equation, and this is what we get. So I'm going to apply A to the left-hand side. So my left-hand side is L acting on y of x. And then I'm also going to apply A on the right-hand side. And so I'm going to apply A of f of x. Now, by the definition of an annihilator, the right-hand side will become 0. So now we have the homogeneous equation A times L of y of x equals 0. And we know how to solve a homogeneous equation like that. We have to take a look at the auxiliary equation and at all the roots. So let's look at this in an example. So we want to find a general solution to y double prime minus y equals x e to the power x plus sine x. Now, in order to find a general solution, we need to know what the homogeneous solution is. So we briefly look at y double prime minus y equals 0. So that's what we'll look at first. And we see that the auxiliary equation is given by r squared minus 1 equals 0. And so that means that r is equal to plus or minus 1. And that gives us the solution for the homogeneous part of this differential equation, that is c1 e to the power x plus c2 e to the power negative x. Okay, now let's take another look at this differential equation, and I'm going to write it in operator notation. So I have d squared minus 1 applied to y of x equals x e to the power x plus sine of x. So now we need to take a look at the annihilator for this part. And the annihilator will be two parts, actually. So we want to get rid of the x e to the power x. And the way we do that is we have d minus 1 because of the 1 here. And then because the x is in front, we actually have to raise that to the second power. And then to get rid of a sign, we then multiply that by d squared plus 1, and that is to the first power. So that's our annihilator for the right-hand side. So now let's apply that annihilator to both sides. So the right-hand side will be 0 because that's how we chose our annihilator. And so now on the left-hand side, I have d minus 1 squared times d squared plus 1. And then the d squared minus 1, I'm going to factor that out and write that as d minus 1 times d plus 1 y of x, and that equals 0 because we annihilated that right-hand side. So we've transformed our non-homogeneous equation into a homogeneous equation. And now we can simplify the left-hand side a little bit because there's a factor of d minus 1 and factor of d minus 1 here. And so if you combine those two, you get d minus 1 cubed times d squared plus 1, and then d plus 1. And now we look at the associated roots. And so that first part here has a root that's r equals 1. If you set that equal to 0, you get 1. And it has multiplicity is 3. So the solutions we get are e to the power x, and then x e to the power x, and then x squared e to the power x. Those are the solutions that are associated with the d minus 1. Now the d squared plus 1, if you set r squared plus 1 equal to 0, then you get r squared equals negative 1. And so r equals plus or minus I, and it means alpha equals 0 and beta equals 1. And so the solutions associated with this part are just sine of x and cosine of x, because the e to the power 0x that comes with that alpha is just 1. And then finally, this last part, d plus 1, that's r equals negative 1, and it has multiplicity 1, so we only get e to the power negative x from that. And so these are ingredients for our general solution. So our general solution, everything y of x equals, we already had this part, so we have c1 e to the power x plus c2 e to the power negative x. And so that takes care of this one right here and this one right here. And then we also have plus c3x e to the power x, that's this one right here, plus c4 x squared e to the power x, and then plus c5 sine of x, and then plus c6 cosine of x. You can flip those around. So we now have our most general equation here. And what you should note is that this part, right, that is our homogeneous solution, and then this part right here, that is our particular solution. Now C1 and C2 would follow from initial conditions, and C3, C4, C5, C6 would need to be solved by plugging in this part, the particular solution, into our differential equation, y double prime minus y equals x times e to the power x plus sine x. And then you have to figure out what those four constants are. So that is a way to use annihilators to get rid of the f, and now solving an equation, a non-homogeneous equation, turns into solving a homogeneous equation, which is just keeping track of the roots. Now, just as a comparison, I'll show you kind of the basic steps of how you would do this using method of undetermined coefficients, at least how you set that up. So if we would use method of undetermined coefficients, and this is just for comparison, because this is not part of the question, but the method of undetermined coefficients, we would also look at the auxiliary equation, right? Auxiliary equation from this original differential equation. Auxiliary equation would be r squared minus 1 equals 0, and that would lead to r equals plus or minus 1. And we would reach the same conclusion about the homogeneous solution. Homogeneous part is c1 e to the power x plus c2 e to the power negative x. But then what we would need to do is we would need to compare x e to the power x with a polynomial of x times e to the power rx. And then what we would note is that m equals 1 and r equals 1. But r equals 1 is part of the auxiliary equation. So then that would mean that our particular solution for that part, that first part, yp1 of x, is then given by a polynomial of degree 1, so that's a1x plus a naught times e to the power x, and then because the root is part of the auxiliary equation, we would have to multiply that by x to the power 1. So that would give us a particular solution that would take care of this part right here. Now, then we would need to compare for the second part. We would compare sine of x with e to the power alpha x sine beta x. And then since there's no e here, we would see, okay, that's alpha equals 0, beta equals 1. So our second particular solution would have this form. Yp2 is equal to b naught of sine of x plus a, well, we can't use a naught here, so let me just use c naught cosine of x. So, and then our total particular solution, yp of x, would be yp1 of x plus yp2 of x. And so that would be a1 x squared plus a naught x times e to the power x plus b naught sine of x plus c naught cosine of x. And we can verify that that is the same thing as we have over here. So if we actually compare the coefficients that we had before, the coefficient in front of the x squared e to the power x, we called that C4, and that a naught x, that a naught was what we called C3 in the previous solution. The b naught, that's actually C5, and the c naught, that's C6. So it's an alternative way of doing the method of undetermined coefficients. We're basically doing the same thing, but with a slightly different way of doing our work.